Gas laws, like the ideal gas law or Avogadro's law, are mathematical statements of the relationship between variables. They don't explain why a certain object, or in this case, gas, does what it does. When we are trying to explain the why or the how, the mechanism for our understanding, we would want a scientific theory. The simplest theory that we can use to understand why many things do what they do is the kinetic molecular theory. We apply it mostly to gases, but it also connects to collision theory that we use with reactions and with kinetics. And it also is related to and can be applied for the motion and properties of liquids and solids. When we think about the kinetic molecular theory, we model the gases as a collection of particles that are in random motion and always in motion. Those particles keep moving until they run into something else, either another particle or the container that they're in. And when we describe gases, we think about three things that we define as true for their behavior. First of all, that the particles themselves are negligibly small. So not just here saying that they're small, but they are so small that we ignore the particle size itself. Particles do have mass, they do move around, but the volume that the particle itself occupies compared to the size of the container is so small that we ignored it. The space between the particles is very large. So when we're doing calculations and thinking about volume, it's always the volume of the container, not accounting for any volume that the particles themselves may take. That's very different than how we treat liquids and solids. They have a defined volume that we can think about and relate to their density and some of their other properties. The average kinetic energy of the particles is proportional to the temperature in kelvins. So kinetic energy, 1/2 mv squared, is the speed or velocity of the particles, also incorporating their mass, is related to the temperature. Most simply, for a single sample of gas, whether that be a pure substance or a mixture, the hotter it is, the faster the particles are moving. Lastly, we treat the collisions as if they are perfectly elastic. For anyone who's taken a physics class knows that collisions can be elastic or inelastic. Sometimes we simplify that by saying they bounce off of one another or stick together, but it really has to do with loss of energy compared to loss of momentum. So we treat it as if there's no loss of kinetic energy. The particles bounce off of one another perfectly and exert no attractive nor repulsive forces on one another outside of that collision. And when we know these pieces of the kinetic molecular theory, it allows us to kind of define or explain all of the different gas laws and behaviors that gases have. The first is simply the definition of pressure. So we have talked about pressure without defining it. Pressure is defined as force per unit area, or how much push there is on a given amount of space. With gases, the force is associated with the collisions themselves as they bounce into one another, or in this case, maybe the container. These particles, as they're colliding with one another, would be bouncing, would be applying force, and therefore would exert pressure. We can talk about that as atmospheric pressure, partial pressure, barometric pressure. All of those are a measure of the collision with the surrounding surfaces. And because we have so many particles with so many collisions on our area or the volume of our gas, we can say that the pressure is likely to be constant until we change another variable. We can explain and understand Boyle's law by thinking about the particles in a smaller space. A smaller volume at the same temperature and speed would result in more collisions, raising the pressure, and vice versa. With Charles' law, at the constant pressure, if the particles are moving faster, they would need to spread out. If they were not able to do that, the pressure and the number of collisions would go up. In Charles' law, we assume that pressure to be the same. We have a container that can change size, so it would get larger to accommodate the faster moving particles without any additional collisions. Gay-Lussac's law is similar. in that a faster moving particle would bounce more often, but this time we have a fixed container. A word we use for that often is a rigid container. So when we're talking about gases in a rigid container, we have defined the volume, and faster moving particles would collide more often. They would also collide with more kinetic energy, and as a result, we would have a higher pressure. In terms of Avogadro's law, and my misspelling here, which has been fixed, the more particles, the more collisions. The more particles, the more space. I saw the word pressure and once again got a little distracted there. So we are trying to keep a constant pressure. We are not allowing the particles to speed up or slow down. So the more particles that we put there would then have to spread out or be in a larger container in order for them to have the same other properties. And with Dalton's law, we kind of already thought of this at the molecular level. It doesn't matter what particles we have, they still collide. When we are explaining things or asked to use the kinetic molecular theory, it's very important that we focus on the motion of the particles and we focus on the particles themselves. We're not talking about macroscopic things like pressure, volume, and temperature. We're talking about the microscopic things like a collision, like a particle's speed, and like the amount of space between those particles. So kinetic molecular theory is all about the motion